Okay, and it looks like we're recording. Okay, so yeah, here's where we ended it last time. We asked some, I think, fairly natural questions about what happens when you go in different directions from a given point in a domain of a function. And it turns out that the answers to those two questions that we asked happen to be the geometric features of the gradient vector, as it turns out. So the direction of the gradient vector was the answer to the first question. This direction is the direction of fastest increase. Very natural question to ask. Very natural thing to want to be interested in. And then, let's see, then we also asked a separate question: how fast is the function changing in that direction? The answer was the other geometric feature of the gradient vector. So this is what I like to call a geometric characterization of the gradient vector. The gradient vector is the unique vector in the domain that points in the direction of fastest increase and whose magnitude tells you how fast the function's increasing in that direction. So one of the cool things about this is, just as a reminder, I think I said this last time, that the gradient to now has been an algebraic thing. At least that's how we've been visualizing it. That the gradient was a kind of a shorthand, right? It helps us write down an algebraic formula in a more convenient way. And we haven't really had much in the way of geometric intuition for it. And now we do. Okay. So moving along with an example now. So we've got a hill that's in the shape of the graph of a certain function. Now again, y'all heard me say it a million times. You always have to be really careful when you're looking at a picture. Make sure you have it very clear in your mind, consciously distinguishing what kind of a picture is this. So let's be sure to note this is a graph. So this is z equals f of x comma y. Right. So we're not looking at a picture of the domain here. We're looking at this weird space that we draw when we're trying to understand what functions look like. The domain, the x and y of it all, as it were, the inputs, just kind of, if you will, the xy plane down here. Okay. Now, before we get into the actual meat of this question, I want to point out a semantical little issue, and that is that we're going to be talking about, a point of, where we are on the hill. Now, here's me on the hill right there, right? I'm on the actual surface of the hill. Right, I'm not buried 150 feet underground. Right, I am on the hill, of course. All right, and yet when we describe our locations, right, in a situation like this, we'll give longitude and latitude. Map coordinates, which in a context like this are kind of morally equivalent to just x and y. Right now, so there's obviously something lacking about this. I live in three-dimensional space. My map coordinates are usually two coordinates, thus describing a point in a two-dimensional world. So that's weird, right? But it's so natural if you think about it, right? Why would anyone ever go to the trouble? I guess I could envision some super weird situation, but vast majority of times when you describe your location, you'd say, I'm at longitude this and latitude that, and no one would add further. And by the way, I am also on the surface of the earth. Right? I have not burrowed 150 feet down. I am not in a hot air balloon 500 feet above the surface of the earth. So very often, just be aware, it is very natural and convenient just to conflate these 2 points. Of course they're not the same, right? But it's so obvious that they're not the same that the context should always be the guide as to which one did I actually mean. So I hope that makes sense. So heads up for that. I'm going to be doing that throughout this exercise, and you'll see this in many other contexts as well. Okay. Alrighty, so with that in mind, I am at the point 1, 3. There it is. Look, I just described my location with 2 coordinates. Of course, that's not where I actually am. I'm actually on the surface. You see what I'm talking about. Okay. So I'm at that point, and I want to know which way is uphill and how steep is it. So, which way is uphill is exactly one of our geometric features of the gradient. Which way is uphill is the direction of fastest increase is the direction of the gradient vector. Right? And how steep is it there? How steep is it there is the slope of the graph, which is the magnitude of the gradient vector. So you see the question that's been asked is really just asking us to, compute the gradient vector and then observe the direction is the direction you want, the magnitude is the magnitude you want. Does that make sense to everybody? Is everybody on board? Okay. All right. So that said, we actually go through it, and here's the function. We compute its gradient, like so. And then you can compute the, which by the way, it's about like that, compute the gradient at the point in question. The magnitude tells you how steep it is. That's just computing the magnitude of that gradient vector. And what direction does this point in? Well, now, with keeping in mind that when you draw a map, the direction of the y-axis is typically what you would call north. And if you think about map directions, if that's north, then the purple direction that we've drawn there, the direction of the gradient vector is southwest. All right, and so southwest. Probably shouldn't use that same color. We'll do it like this: southwest. All right, is everybody happy? Okay. Yeah. Good deal. Okay, so now moving along. So let's talk about level sets. There's a neat observation to make here about how level sets relate to gradients. This is another geometric interpretation of gradients. You might say another bit of the calculus of level sets, right? Because gradients are objects of calculus, and the interpretation that we're going to understand in the context of level sets makes this calculus of level sets. So that said, suppose we have a differentiable function. Fine, we're looking at a certain point on a certain level set. Now, again, I remind you, very important, when you're looking at a picture, as we are here, you've got to remind yourself, what kind of a picture am I looking at? This is a level set. This is not a graph. Right? This is not height as a function of x and y. Right? This is a level set. We have a function of 3 variables that I've drawn a picture of here. Right? So I just want to make sure to keep that in mind. Okay. So the observation we make here, this is kind of a nice observation. If I am on the level set, such as at that point, and I emphasize this is a level set, so f is constant on that level set. Now, if I am moving within the level set, let's say like that, for example. Now, this is my attempt to draw a curve that is moving entirely within this surface, so on this surface. Right? Let's ask the silly question here. What's the value of f at this point on the curve here? Well, on the level set, the value of the function is c. What about if I move over to here or to here? On the same level set, f is still c. And as I move along to our point in question, a, or as I move beyond that, as I keep moving, f, it remains c. That's what a level set is, right? The whole point of a level set is that as you move within the level set, the value of the function doesn't change. And so I'm going to make the observation here that if the function is constant as you move, then another way to say that is that the derivative is 0. Right? So at this point, let's see here again. So at this point, and as I move in this direction, tangent to the curve, and therefore tangent to the level set, in that direction, the directional derivative is 0. df ds is 0. Okay. Now, here's the thing. That applies to that vector, but it also applies to, if you think about it, let's see here. Yeah, I guess I have to do that again. That's fine. It also applies any other tangent vector. Whichever tangent vector you might entertain, well, any tangent vector to this surface at that point represents moving along the level set where the function's not changing, and again, therefore, directional derivative is going to be 0. Okay. Fine, so what? Who cares? Well, here's the thing. If the directional derivative is 0, and if directional derivatives are computed with these special dot products, as we talked about last time, well, that means that these dot products are 0. And if the dot products are 0, then we have a geometric interpretation. Dot product equals 0 means that those two vectors are always orthogonal. So, neat fact, powerful fact, gradient vectors are always orthogonal to tangent vectors to level sets. Or, as we like to say casually, gradients, if they're perpendicular to all of the tangent vectors to the level sets, then gradients are perpendicular to level sets. And that's the picture that we draw down here. So, in fact, here, let me color this a little bit differently. If the gradient is perpendicular, I got to do this with, here we go. If the gradient is perpendicular to all of the tangent vectors, right, then the gradient itself, let's see here, color choices, the gradient itself has to be perpendicular to the surface. Yeah? So, neat fact, again, important geometric interpretation. Why won't this? There we go. Important geometric interpretation of gradients. Gradients are always perpendicular, as noted there, to level sets. Cool. Neat fact, again, calculus of level sets. So there's a nice application of this to the question of tangent planes, and you may be thinking to yourself, we already know how to write the equation of a tangent plane. Yeah, sure. I'm going to show you a different way to motivate the exact same result for the equation of a tangent plane. This one is arguably easier. As it turned out, there was actually a fair amount of development that we had to sort of go into to come up with our formula for linear approximations, and it's fine, it's doable, right? But there's something really quick and elegant about what we're about to do here. The big idea, and I'm going to let y'all wade through the details on this. I think it's very wadeable, right? No big deal. I just want to hit the highlights here, and that is if you are looking at a graph. Now again, this is our typical. Whoops, I wanted to be in highlighter mode. If you are looking at a graph, as we do when we're talking about linear approximations and tangent planes and stuff, right? Looking at a graph, being as it is a graph, that means we've got z equals the function of x and y, whose linear approximation we're going to be making reference to. The innocent observation is that, well, if it's a graph, it's also a level set. Right? And this is one of the examples that I made a vague reference to some time ago, and I remember I showed you this trick that anytime you have a graph, you can just kind of move terms around a little bit, seemingly hardly changing the equation at all, but what had been viewed as a graph, we can now reinterpret as being a level set. of a different function, of course. Yeah. But still, what had been viewed as a graph, we're now viewing as a level set. So with all of that setup having been done, I'm now going to completely abandon all this graph point of view. We have a surface here that is a level set. That surface is a level set. I'm interested now, apparently, so it seems, in finding the equation of a tangent plane to a level set. How am I going to find the equation of the tangent plane? Well, I'm going to need to find a normal vector to that tangent plane. Now I appeal to the picture, your sense of geometry. If you're looking for a vector perpendicular to the tangent plane, you're looking for a vector that's perpendicular to the surface itself. Let me say that one slightly different way. Then you're looking for a vector that's perpendicular to a level set. And that's the tool that we just discovered on the previous page. Gradient vectors are perpendicular to level sets. Right? So I'm going to be able to, let's see here, let's squeeze all this in. There we go. This vector that's going to count as my normal vector for my tangent plane, that vector, I can just use the gradient of the function whose level set I'm looking at. And again, this is very important, very important. This is not f, right? This is a graph of f. I don't want to talk about graphs. I want to talk about level sets. Level sets, the calculus of level sets is what has this amazing feature about gradients being perpendicular. Right? So what is this surface a level set of? It's not f. It's a level set of z minus f. So all we have to do then is compute the gradient of, let's see here. I need to compute the gradient of z minus f. And you can just think through now what happens when you take the various partials. By the way, notice this is a function of 3 variables. Again, we're no longer looking at f. F was a function of 2 variables. The function whose level set we're interested in, the function whose gradient we need to compute. Function of 3 variables, x, y, and z. And note in the formula for this function, x, y, and z partials you can just write down. And now it's kind of all over, but the shouting and the celebrating. So let's see here. We have our normal vector. Let's see if I can fit all this in here. Here's our normal vector, right? And n is what goes there in the equation for a plane. Here's the equation for a plane. So n goes there, and then let's look back up to the picture we had. I need to talk about x naught. X naught, a point in the plane. Well, I'm going to take that point. That point right there is, now you might say in graph speak, right? In graph talk, this is the point above this point on the domain, which means that the x and y coordinates are a and b. The z coordinate is whatever the value of the function is. So that point is a comma b comma f of a b. Oh, can I get this? Why isn't? Oh, there he goes. Okay. So that is what goes there. And then dot it out, move terms around. Again, this is very weightable. I want y'all to wade through the rest of this. And what comes out for the equation of that tangent plane is this very familiar formula down here. I want to go. Okay, come on, pinch. There we go. Okay, so nice application. Calculus of level sets was the tool that made this all possible, specifically understanding that in the calculus of level sets, gradient vectors are perpendicular to the level set. Okay, this example right here, I'm going to wave my hands at. Again, this is very readable. This is just explicitly an example of what we did on the previous page. There's nothing happening in this example that isn't on the previous page. All right. So we're going to move on now to the very last topic for Chapter 2, and then we're going to move into Chapter 3. Fingers crossed. I hope we get there. We're behind schedule in class, but we're going to catch up. One of the ways that I catch up is, again, I have to make tough decisions about what we spend class time on, and so the ideas and sort of the big worries of why we care about the implicit function theorem. Sadly, that's on the low end. If time permits, then it's just barely above the bar, unfortunately, and so when time doesn't permit, I think it's a little below the bar. So I'm going to be quick about the sort of the background and context, but I do feel like I need to say a couple of words about this. And we look at a situation like this. Notice I'm starting off with a curve written as a level set, and now I want to ask a different question. Can I view this as being a graph? Well, no, of course not. Obviously, it fails the vertical line test. That's silly. Okay, so what I meant, though, what is a significant question is, can I view this locally as being a graph? Now, let me expand on what I mean by locally. What I mean by locally is if we're looking at a particular point, and if all I care about is what's happening near that point on this curve, and I'm highly myopic in this scenario where I don't care about what's going on up here. All I want to know is what's going on near this one point. That's it. Right? Now, in that situation, let me redraw our picture now. Redrawing, I no longer care about most of this curve. Now I only care about just the part of that curve that's in that little yellow ball. Is this locally a graph? Can I, in other words, on this little piece of curve, can I view y as being a function of x? And in this case, yeah, of course, yeah, passes the vertical line test, no problem, right? Here's it passing the vertical line test with flying colors, no issue. Likewise, if I were to look over to here, locally, is this part of this curve, does it pass the vertical line test? Yeah, no problem. Cool, right? Seems like this is going to be pretty trivially easy to do, but now let's look at this point right there. And I emphasize we're only looking at just the part of the curve that is nearby in whatever sense, for some sufficiently myopic, looking only just within a certain distance of that point. Can I view that as being y being a function of x? No. Crash and burn, right? It does not pass the vertical line test. And so no, here I cannot, not even locally. The issue isn't stuff happening down here and intersecting 3 times. No, the issue here, how this fails. I cannot view y as being a function of x because no matter how close I get, no matter how myopic I am, there will be failures of the vertical line test. Oh gosh, there we go. Failures like so. Right, and you could imagine as you get closer and closer, but look, let's get even more myopic. Let's just look really, really close to this one point. Same problem. It just doesn't go away. So not even locally, for a point like this, can you view y? Oh gosh, sorry. Can you view y as being a function of x? Yeah.
Are there bounds to what we define as local?
It's context dependent. So basically, locally says whoever is doing the talking gets to decide, gets to make the little radius as small as they need to for their purposes, right? And so, for example, at this point, let me clean up here. At this point, it's not good enough. Sorry. I wanted to be in highlighter mode. At this point, this is small enough, but this isn't. You know what I mean? And so, okay, well, that's too big, so I'm going to make it smaller. And if some little problem were to arise here, then I could say, fine, let's make it smaller again. I get to make it as small as I want to. And the point is, in this case, the failure that this point leads us to is that it doesn't matter how small I make it. Even if I have complete control over how small this little yellow region in consideration is, I can make it as small as I want. There's no way I'm ever going to be able to view this as being a graph. Is that cool?
Yeah, would they be like on the domain? Like, would that restriction be set on the domain? Or you mentioned like radius. Is that like for this?
Typically, when we say locally, we're talking about within some ball, some little disk. But again, it's speaker's choice, and I don't even have to say what it is at any point. It's just that I always have the right to just make that as small as I want to make it. Yeah, right. Okay. So now, next question, important question: who cares? And a lot of people would say, yeah, who cares? What's the big deal here? The big deal is. Typically, in a case like, let's see, let me go back to the highlighter. If you're talking about a point like this, if you can locally talk about y as being a function of x, then you can talk about the slope of the tangent line. And hey, if this is a graph locally, all I need is locally. If this is a graph, then the slope of that tangent line is dy dx. And I can talk about dy dx because y is a function of x, at least locally, near that point. So dy dx is a meaningful thing at a point like that. Y is actually a function of x. But if you are looking at a point like this, where y is not a function of x at all, in any sense, no matter how myopic you are, then dy dx is meaningless garbage nonsense. And a lot of people get this wrong. A lot of people think, oh, well, wouldn't dy dx just be infinity here? And it's not. Y is not a function. Dy dx is notation representing taking a derivative of a function. If y is not a function, you can't take a derivative of it any more than you can take a derivative of a bicycle. It's not a function. We can't take derivatives of bicycles, and we can't take a derivative of y here either. So this is a nasty little problem, right? Because we are fairly accustomed to writing down things like dy dx, and what we find ourselves now in a situation where we can't even write down dy dx. It's not a thing, right? So nasty problem. So what we're going to try to do is figure out a way around this problem, and here's the way it should be done. Wow, this is my take. This is a point of view that is all too often left out in single variable calculus classes. It's left out understandably. You'll notice I'm about to make a reference to a gradient vector that doesn't come up in single variable, right? So you can't really, but high school calculus classes tend to just have to therefore gloss over this really important point about when a variable is or is not a function of another. So here we go. If we are in a situation like this, where what I would call, we have a problem, right? This is one of these points where I cannot view y as a function of x. If you have a problem, notice, and again, geometric appeal, I don't want to get all rigorous about this. But geometric appeal, the problem is the curve is wrapping under itself. But that's why you fail the vertical line test, is because it's wrapped under itself, or over, if you prefer, it doesn't matter. And if the curve is wrapping under itself at that particular moment, then I would argue that you could interpret that as saying, well, that means I have a vertical tangent line. But wait a second, if you have a vertical tangent line, that means that the gradient has to be horizontal. Now wait a second, if the gradient is horizontal, let's just kind of following it through, and don't forget what the formula is for the gradient. The gradient is partial of f with respect to x, partial of f with respect to y. If that's horizontal, horizontal means that the vertical component is 0. Everybody with me so far? So basically, anytime you have a problem, that's going to force the y partial of f to be 0. Everybody on board? All right, so now I'm going to do another contrapositive move. If problem means that y partial is equal to 0, well, then in any situation where the y partial is not 0, then you couldn't possibly have a problem. Does that make sense to everybody? Contrapositive is a really nice, really important idea to have, comfortably digested in your mind. It comes up and is useful in a lot of situations, such as this one. Okay, so this is what we're going to use most of the time. Not so much this. This doesn't really resolve a question for us. This, what I haven't read here, assumes that you already know whether you do or don't have a problem, and then tells you something that answers a question you didn't ask. Right? This, what I have in green, is what's useful. There's an algebraic test that I can perform. I can compute a really easy partial derivative. I can look and see if it is or isn't 0. And if that checks out, if it's in particular, if it's not 0, then I get to conclude that there is no problem that y is a function of x. I am absolutely at liberty to talk about dy dx because y is, locally at least, a function of x. So here's the three-dimensional version. Now, real quick, everything here and prior arguably coulda, shoulda. I understand that it can't, right? But this addresses a version of the implicit function theorem that you may have at least seen someone wave their hands at in a high school calculus class, and I hope this tidies that up a little bit for you. Here's the three-dimensional version. So this is now, of course, would never be discussed in a single variable calculus class in any sense. Suppose you have a level set, again, as usual, some function being equal to a constant. And let's ask some of these same questions. I'd like to know on this level set, let's say at, let's say at this point right here, can I locally view z as a function of x and y? And locally, near that point, yeah, sure, that's no problem. You could imagine little vertical lines going through there, and it's no issue, right? Z is clearly going to be a function of x and y there. And likewise at most other points. Let's see here. Likewise there. Likewise there. Likewise most other points. But where it becomes a problem is, is here. A point like that where the surface is in the process of wrapping under itself. Now it's a little bit harder to draw the picture here. I'm going to appeal to your intuition. Where the surface is wrapping under itself, you're gonna fail the vertical line test again. It's sort of a three-dimensional version of the failure that we saw previously. Let's see here again, drawing pictures. The surface is in the process of wrapping under itself there. That means that it has a vertical tangent plane, and that means, keeping in mind that gradients are always perpendicular to surfaces and therefore perpendicular to the tangent planes, that means that gradient must again be horizontal, and in this case being horizontal means that the z partial is equal to 0. So we find ourselves in this same scenario, that a problem means that this certain partial has to be 0. So we say the magic word contrapositive again, and if the z partial is not 0, then there's no problem. And again, that means that we can, take derivatives to our heart's content. Let's see here. Before I get to the statement of the theorem, let me point out in both of the examples that we've seen here. Let me clean up my picture here. If you're concerned about y possibly or not being a function, it's the y partial that you need to look at. Notice in our three-dimensional example here, we were wondering about z possibly or not possibly being a function, and it was the z partial that answered that question. Right? And I'm just going to kind of wave my hands here, and again, I don't want to get too rigorous about this, but I claim that that's a pattern. And whichever variable it is that you're wondering, can I treat it as a function? By the way, the tip-off is going to be whichever variable it is that you're going to want to take derivatives of, right? Keep in mind, you can only take derivatives of functions. So whichever variable you want to take derivatives of, that's the one you need to worry about whether it's a function, and that's the one with respect to which you need to take a partial of your original f, the function whose level set you're looking at. So that's what you'll notice in the statement of the theorem here. If you want to be able to view x sub I locally as a function, then you need to take the partial with respect to x sub I. And if it's non-zero, then that means that you can view it as a function as such. Everybody with me? All right, so here's an example. We've got a surface given to us, some wacky surface. And by the way, I emphasize, I really don't know what this surface looks like. Don't try to draw this surface. It's weird. It's cubic in more than one way, and it's not written as a graph. Oh my gosh, this is wow, super weird, right? Okay, so let's ask the question: is x locally a function of y and z? Now, notice they did not ask, can I solve for x algebraically? Do I have the algebraic chops to be able to actually solve for it? Not at all what's being asked, right? But just hypothetically, could it be viewed as a function independent of whether or not I have the algebraic chops to be able to actually solve for it? Okay. All right, so the way forward, per our short summary from the previous page, whichever variable you want to view as being a function, I am interested in viewing x, perhaps, hopefully, fingers crossed, as a function. Take the partial with respect to that variable. So I want to view x as being a function, so I'm going to take a partial with respect to x. And the algebra of that, of course, is just the kind of typical stuff. Keep in mind, we are taking the partial of the function whose level sets we're looking at. This is, of course, very important, right? The premise of all of this is that we're looking at a level set of a capital F function. So we're going to take the partial of that function with respect to x. Is everybody happy? Cool. A little bit of algebra. No big deal. There's your partial. We're interested in what's happening near this point 1, 2, 3. So we've got to plug in that point 1, 2, 3, you notice. I'm going to plug in x equals 1, y equals 2, z equals 3, and this partial then turns into 4, otherwise known as not 0. And so, cool, we win. Yes, I can view x as a function of y and z, at least locally. Everybody happy? All right. Okay, so that means I'm allowed to take derivatives of x. I can talk about, for example, I can talk about the partial of x with respect to y, because x is a function. I can talk about the partial of x with respect to z, because x is a function. Totally fine. Now, next question. How would I actually compute that derivative, right? Let's notice in this example here, yeah, I guess it's nice to know that I'm allowed to take the partial of x with respect to something, but I can't solve for x in here. How am I going to take a derivative of it if I can't even solve for it, right? So there's a couple of different points of view you can take on this. This is a point of view that is a little bit more careful than what I'm about to show you. And you can look at this. It's ultimately equivalent to what I'm about to show you, but I'm not going to go through this because it's unnecessary. There's a whole lot going on here that adds to the scariness of this particular slide, right? That doesn't actually affect the computations, right? So here's the point of view I'm going to show you. It's like this. We've got this function, capital F, that's required to be a constant. I am apparently interested in taking a partial of x sub I because, after all, it is a function of the other variables. And so let's just think about what happens if I'm taking its partial with respect to, let's say, x sub j. Here's x sub j. And so I want to look at this green function that I have over here, weirdly drawn, admittedly, right? But I'm going to change this input xj, and I want to know how xi changes as a result. And one of the first things you're going to notice about this diagram is it doesn't follow our rules about how to use the chain rule. The arrows are all messed up, right? And this diagram needs to be fixed. One could argue, but this is the fix, and again, you can take a look at this if you'd like, but I don't think there's much reason. Let me just say that this fix confirms that I can just kind of think through the different paths here, and that there's really only two possibilities of how changes happen to f here as xj changes. On the one hand, changes can propagate along that path, which gives us that term. On the other hand, changes can propagate along, color choices, along that path, which gives us that term. And again, I know I'm violating my own rule here about make sure that your diagram is actually a composition of functions. And again, it is. I don't want to get bogged down in the ugly, that's all. Right? And so if you want to keep track of how much capital F changes as xj changes, here's the formula, but wait a second, capital F is constant, right? That was what defines our surface in the first place, is that capital F has to be constant, and therefore this partial of it has to be 0. And so with that having been noted, notice that the partial derivative you want to compute is right there, and it's easily solved for, and you get this formula then for how to compute that partial. So now again, there's different ways that you can compute implicit partials. I think this is the easiest one to work with in practice. Notice all you have to do is take a couple of partials of the capital F that you're given and then plug into this formula. Everybody happy? All right, now do notice, very importantly, and this is huge. This is huge. So many students get stung by the following. This minus sign right here. Pretty counterintuitive, especially if you rely on inappropriate interpretations of the notation. And y'all may recall I spent some time when we first started doing the chain rule emphasizing that these are not fractions. Right? This thing right here, this is not a ratio of two well-defined things. These are participants in different stories. this partial f right here is not the same as this partial f right here. They're not the same at all, right? So it's tempting, so tempting. But don't do this. This is garbage nonsense. It's tempting to cancel the partial f's and to then say, hey, this is in the denominator of the denominator and therefore is my numerator. And let's see here, this is the denominator of the numerator, therefore it's my denominator. And looky there, doesn't it look like this fraction ought to simplify to the partial that I'm interested in? No minus sign involved. Very tempting. And fundamentally garbage. It's just meaningless nonsense. It doesn't make any sense at all, right? So here's the problem then. If you make the mistake of forgetting the minus sign, let's just suppose that you forget that minus sign there, and you compute your partial with this fraction of partials, no minus sign. It makes it look like you think you could actually cancel the partials, which is, again, total garbage, right? So this is why I say this is a very delicate, this is a very dangerous formula to use, in the sense that you're one accidental minus sign away from writing down nonsense, like importantly bad nonsense, right? So don't forget that minus sign. If you remember this minus sign, then you're just using a standard formula. No problem. It's all good. Full credit. Right? If you forget the minus sign, then it looks like you have no idea what's actually going on. And again, from a grading point of view, that's really, really bad. One of the most important minus signs in the course, right there. That makes sense to everybody? So I make a big deal out of this in the hopes that as few people as possible will forget that minus sign. Okay. All right. Okay, so let's see an example. Now we've already seen this surface right here. This surface right here is the exact same surface we were looking at a minute ago. And recall that we've already established that near this point x is locally a function of y and z. And again, that's what we established in our previous example on the previous page. So knowing, as we did, that x was locally a function, we are therefore entitled to ask, perfectly reasonable question, what is that partial derivative? And I'm going to use the formula that we just established. Here's that formula. Now the variables here aren't xi and xj and stuff like that. Right here, the variables are x and y and z, so I've adapted the formula appropriate to what the variables are that we're actually interested in. The nice little memory tool for this, of course, is that whatever is the variable on top, that's the one that goes there, and whichever variable is on the bottom, that's the variable that goes there. It's the wouldn't it be nice if these actually were fractions that I could play cancellation games with, as we established that we couldn't. So you write that down, and then again, don't forget your minus sign, right? Make triple sure to remember that minus sign. Everybody on board? Everybody good? In fact, word of advice, I would encourage you to, as you start to write this formula down, don't start thinking first about which fraction are you, which partial divided by which partial. Write the minus sign down first. Get that minus sign on the page, right? In fact, conceivably, I wouldn't be stunned that if you were to write down just this, and then you ran out of time and didn't have time to think through the rest of it, you'd probably get a little partial credit. right? Okay, so get that minus sign on the page, and then think through again denominators of denominators and stuff like that. These are easy functions to take partials of. Again, f is that thing. You take the z partial, you take the x partial, you divide as indicated, you carry your minus sign through, and then you get your eventual answer right there. Okay. All right. Let me make a really, really quick pitch on one thing. I just want, I want to make sure that everybody's clear that when you do an implicit differentiation problem, you really do have to do this thing about checking whether the thing you're going to take partials of is actually a function, right? If you don't establish that it's actually a function, then you're writing down just wishful thinking, right? So if I were to, up here in this first example, if I were to skip all of this, never ask if it's a function, never go through this process here, none of that. If it were not given that x is locally a function like it was in this sort of like the second half of the problem, if you're just given us an equation representing a surface and they ask you for the partial of x with respect to z, the very first thing you should think is, what are you talking about? What do you mean partial of x? X isn't a function. X is a variable in an equation. Where do you get off asking for the partial of x? We don't even know it's a function. Right? So that's the first thing you have to do. You have to, very importantly, first establish that the thing in question even is a function. And then once you've established that, then you can go through and do the computation. And just from a grading point of view, just FYI, these are roughly equal parts. So if this were a 20-point question, probably about 10 points would go to the establishing it's a function, and about 10 points would go to the actual differentiation. Yeah?
If x wasn't locally a function, you should just get a 0 in the denominator, and then you use it itself.
Yeah, I hear what you're saying, but let me translate that in a unfriendly way. But if I write down the garbage that makes no sense, won't I discover it later? And that's really, in mathematicians we just don't do that, right? And so I totally hear where you're coming from. And again, if your focus is on the answer at the bottom of the page, then what you say is reasonable. But it isn't, right? We're all about reasoning, and so we can't do that. Y'all have a good day. I'm sorry to go over. See you later.